Hello everyone. Today I would like to present OmniActions, predicting digital actions in response to real-world multimodal sensory inputs with large language models. This is work done during my internship at Meta Reality Labs in collaboration with Yan Xu, Tovi Grossman, Stephanie Santosa, and Michelle Lee. People can interact with the real-world information using their mobile phones. For example, if you see a famous landmark, you can take out your phone, take a picture, and then either send it to a friend or post it on social media platforms such as Instagram. In the era of pervasive augmented reality or always-on AR, people can continuously interact with the information without interrupting their current activities. For example, if you see a stunning sunset on the beach with AR glasses, you can simply activate them to capture the moment directly into your album memory instead of having to pull out your phone, launch the camera app, and take the photo. However, such interactions go beyond merely capturing the scene and save it. For example, when you are in a grocery store, you may desire different types of interactions with the environment. For example, you may look for more information about the orange, such as the calories, or you may want to do some price comparison of different wafer sticks. Or you may want to recognize the categories of veggies as you have not seen before. Other than such visual information, the grocery store may be playing some background music that you are familiar with, and you may want to recognize the name. Such interactions are defined as digital actions in the vocabulary of our paper. And the raw real-world information, such as what the user is seeing and hearing, is referred to as multimodal sensory inputs. However, common interaction methods with AR devices such as speech or hand gestures may not be feasible in many everyday situations. For example, users engaged in physical tasks may find their hands occupied, and rendering hand gestures for AR interaction become impractical. And similarly, when individuals are cognitively or socially engaged, such as during meetings, using speech for interaction might be inappropriate or disruptive. And therefore, the goal of this work is to find a way that, given different types of multimodal sensory inputs, future pervasive AR devices are able to predict what digital actions the user would like to perform on such information. And additionally, such digital actions should be grounded as executable actions for different apps and tools. For example, a digital action to identify background music should translate into actions such as opening the Shazam app and initiating song recognition. Similarly, if the digital actions involve saving the price of wafer sticks, the corresponding actions will involve extracting the text and adding it to a list for future reference. And in practice, these executable actions are developed by programmers who integrate these commands with the functionalities of different mobile applications, thus to ensure that the supported functionalities could cover a holistic range of actions that user may intend to perform during real-world scenarios. A design space of potential digital actions is needed. However, there are several challenges. The first one is that there's no existing design space of digital actions in the pervasive AR settings, and there's also no existing dataset available that we can code a design space out of it. Therefore, in order to generate such a design space, we need to collect new data on what types of digital actions the user might want to perform when they are interacting with the information in the world. However, this poses another challenge, that is, it is hard to simulate the settings of pervasive AR, as unlike smartphone nowadays, there's no widely available AR devices that general users have access to and collect data. And to address this, we designed a diary-based approach to collect data from general users. Specifically, we adopted a snip-based diary technique to collect the data from users. Instead of reflecting on captured data at a fixed time of the day, the participants are asked to log data whenever they encounter information in the world that they wish to take action upon. This helps simulate the always-on features of an AR platform, where users can interact with AR interfaces anytime and anywhere. We recruited 39 participants with diverse demographics groups to reflect genuine needs of general users. Each participant was asked to upload 10 data entries in a period of 5 days. And here is a simple data entry. Each data entry consists of the actual media. Note that if the user would like to take action on audio data, they will instead write a short description of the audio information. For example, if they hear bird chirping, they will just simply type bird chirping. And also contextual information, as we assume that contextual information would actually affect the user's desired actions. And also, we collect which part of the information that user wishes to take action on, and the actual actions, as well as the high-level goal and the reason of taking the actions. As you can see from the slide, users can choose the labels of the action based on their actual intent, which will serve as a reference point in the later process of open coding the design space. Such predefined labels were generated from an internal formative study. For more details, please refer to our paper. In summary, we collected 382 data entries in total, and using the collect data, we coded the final design space of the digital actions on multimodal sensor inputs. The design space consists of 7 general categories and 17 specific categories. And this is the data distribution of each category. One observation from the data is that there are several more popular actions such as share, save, and lookup, while the remainder types of actions are less common. Additionally, we observed that participants tend to take multiple actions in succession. And here we also observed that participants use different patterns of follow-up actions when interacting with data from different modalities. The overall follow-up actions when the target was visual versus audio was similar, but there appears to be a difference in certain actions. For example, transcribing is exclusive to audio, and therefore there is no transcribe actions when the user's target information is visual. And using the design space of the digital actions, we also develop a pipeline for the end-to-end prediction. Specifically, the system leverages the state-of-the-art AI models to understand the visual and audio information from different hierarchy and convert them into structured text. Then the pipeline feeds the structured text into a large language model to perform reasoning and predict the action grounded in the design space. Using the data collected in the diary study, we performed the technical evaluation on using different approaches. Such approaches include traditional training and intent classifier using the data, or fine-tuning a language model with or without chain of thoughts, or using the in-context learning-based approach to prompt a large language model. The result shows that even without fine-tuning, the large language models can achieve really competitive results. For more technical details and discussions, please refer to our paper.